Hi there, everybody. Welcome to Chem Complete, and this is going to be the set of general chemistry lectures for Chem Complete. So I just wanted to introduce myself. My name is Professor Tomney, and I will be walking you through the general chemistry curriculum that I've designed for the Chem Complete series. So the goal here is going to be to deliver general chemistry content starting from what you would normally find at the beginning of any type of college textbook all the way through the end of that college textbook for general chemistry. There are organic chemistry. I hope to at some point do an analytical chemistry series. However, you should go and check those out separately. This is going to be strictly for general chemistry. You could apply this potentially to AP chemistry or high school chemistry if you were taking a course like that. And we'll go ahead and get started. So this is going to be the opening lecture for general chemistry. So the first question that always comes up is, what is chemistry itself? We have to understand what chemistry is if we'd like to study chemistry. And what chemistry is, a lot of students will say it's the study of chemicals, it's the study of atoms. Those are good ideas, but that's not correct. Chemistry, the atom definition was a little bit closer. Chemistry is the study of matter. And specifically, it's going to be the study of the properties of that matter and what changes those properties can undergo, or what changes that matter can undergo. So we talk about physical and chemical changes. We'll talk about that a little bit more in the next lecture. But right now, what we really want to grasp or understand is that chemistry, the study of chemistry, is the study of matter and the changes that that matter can undergo, because we're going to talk about eventually chemical reactions. Whenever we get to things like organic chemistry, we're talking about organic reactions. Organic chemistry is renowned for what's called organic synthesis, changes in compounds in living systems. So if you see me glancing over here, I've got a list of topics I want to cover. So that brings up the next question, which is, okay, so if chemistry is the study of matter, then what is matter? I have to define what matter is. And matter, a lot of students like to say matter is everything. You have to be careful because everything would include everything. So something like a vacuum out in space would not be considered matter. We do have a definition for matter. But most things are going to be considered matter, certainly at least that we come across in our everyday life and in our plane of existence that we can confront and interact with is going to be classified as matter. So matter is anything that has mass and occupies a volume or occupies some amount of space. Those are the two requirements to be considered matter. Now, we're not really going to get into in this class dark matter and antimatter and things of that nature, which certainly theoretically exists. You could talk about that in an upper level physics course. We're talking about physical matter that we interact with on this plane that we can see, measure, utilize, etc. When we're talking about something that has mass, you should not confuse mass with weight, because weight, and a lot of times these two sort of get interchanged. We talk about taking the weight of something. So, you know, what's the final weight? You really should be talking about what's the final mass. Now, it's difficult because weight deals with the gravitational pull on a given mass and how it affects that mass. So yes, when you step on the scale at home, you are taking your weight. You're technically not taking your mass. You're taking your mass as it is represented on Earth, which is your weight on Earth. Okay, your mass does not change when you change locations. Now, let's use an inanimate object because a human being can lose weight. So if I take some sort of a figure, an item, right? So here you go. I have a little figure on my desk here. If I take my little figure, which is not going to change over time, it's going to contain the same amount of mass, and I weigh this figure on Earth, it's going to have some weight. And then if I take this figure to the moon and I weigh this figure on the moon, it's going to have a different weight because the gravitational pull on the moon is not as intense as it is on Earth. And then I could take this to a different planet where maybe the gravitational effects are more intense, a very dense planet, something like Jupiter perhaps, and then I have an even greater gravitational pull on this figure, so it's going to weigh more in that case. Okay. However, the mass, the number of atoms that make up this figure and the space that this figure occupies is still going to be the same from planet to planet to planet, right? It's not changing. This doesn't become half the size when I take it to the moon. It may weigh less, but its mass, the number of atoms that physically take up and make up this character, okay, are going to be exactly the same no matter where I am. And so that's matter. You have some given amount of mass, and when we deal with mass, we're going to have a unit at some point on what's called SI units, or standard international units. So we don't do mass in pounds when we're dealing with chemistry. You deal with grams and kilograms. Volume, because that's the other part of matter, we're talking about volume and occupying some volume, is dealt with in liters or milliliters, not... and again, you can use different versions, but we use the metric system in chemistry. So we're not really going to deal with gallons and ounces so much as we're going to be dealing with milliliters, liters, things of that nature. Okay, so that's matter. So if we understand that matter is anything that takes up space and also has a mass, the next question is, well, what is it that contributes to mass, right? What is it in matter that gives it mass? What is it that actually occupies that space? And the answer is, now we're getting ready to talk about atoms, okay? So atoms, by definition, are the simplest building block that you can get when you're dealing with matter, right? So if you imagine you're playing with Legos when you're young, or any other type of set like a Connect set or something like that, the simplest parts that you can get, that's what's going to build the entire set, right? And so atoms, when we're dealing with everyday materials, atoms are the simplest unit that we can get. That's what we build from the ground up, and then we get the nice molecules, compounds, and eventually matter, or things that we interact with in our everyday life. And so atoms are those basic building blocks. Yes, there are units that are smaller than an atom, but they come together, and the atom is really the full functioning minimal part that you need in order to continue forward with building matter and working with chemistry and so forth. So you can talk about, and we will talk about in a future lesson, protons, neutrons, and electrons, right? And those are the building blocks for the basic building block. But we tend not to deal with lone electrons or lone protons. Not to say that they can't exist, but they're not really going to be contributing to matter. We don't see giant clusters of electrons and consider that to be matter. It's protons, electrons, and neutrons all put together, and then we combine those atoms, and we can mix and match those atoms to make compounds, and then we're talking about matter that we're looking at, right? So what's the difference between an atom and an element is one of the next questions we come across, because a lot of times you'll say, well, what is an atom? And people say hydrogen, helium, nitrogen. Yes, those are all examples of atoms. Those are elements, okay? So an atom is the basic building block. It has those components we just talked about. An element is going to be the simplest chemical form of an atom that cannot be broken down any further, right? So when we're talking about things like oxygen, nitrogen, hydrogen, any of those elements, an element is the simplest chemical form that you can get for an atom that cannot be broken down any further. So for example, if I talk about H2O, which is a compound, water, H2O can be broken down into hydrogen and oxygen. Those are the respective elements that come together to form water. So once I break water apart into hydrogen and oxygen, at that point, I'm dealing with hydrogen atoms, basic building blocks, oxygen atoms, basic building blocks. I have to be able to put those back together in order to get the compound. They are elements when they're standing by themselves, okay? So let's see here. We talked about matter and elements and atoms. What we just started to talk about was molecules. And molecules, when we deal with molecules, compounds, you can use, there's several different interchangeable words. We're dealing with a makeup that has more than two atoms. Okay? It doesn't always have to be two elements, because you can have two atoms that are the same that come together to form a compound. So for instance, oxygen, the type of oxygen we breathe, is O2. It's not just oxygen O. And so two oxygen molecules coming together, or I should say two oxygen atoms coming together, make a molecule of oxygen, the type that we breathe. Same thing, in fact, most of the air that we breathe is the inert gas nitrogen. It's not oxygen. Oxygen's only roughly about 21% of the air that we breathe. And so when we talk about breathing air, the bulk of it being nitrogen, nitrogen gas is N2. It's two nitrogen atoms put together to make a nitrogen molecule. Okay, so keep in mind, elements cannot be broken down any further. So when I have a nitrogen atom, I can't break that down into simpler elements. It's already at its simplest form. And I can take some of these elements and put them together to create compounds, right, or molecules. So that's starting to build up, and then we can make very complex molecules, something like cholesterol or a very large molecule, or other steroids, and then we can have very simple molecules like water or the oxygen we breathe or things like that that we were just talking about. Now, I want to bring up a point here, and that point is that a very, very small change, just exchanging one element, can have a huge effect on how a molecule is going to behave. So let's take a quick look at that on the whiteboard here. Okay. So, for example, let me bring this up. For example, if I have H2O, and I'm not going to get worried about all of the different electrons and the bonding structure. These are not going to be correct structures necessarily from a Lewis structure standpoint, for those of you that may know what this is, because this is the beginning lesson. We're not really there yet if you were running through a general chemistry course. Okay, so here's water, H2O. So it's hydrogens bonded to an oxygen. If I change out one of these H's for what's called a methyl group, a CH3, I end up with methanol, the alcohol. These are two very, very different functionalities when I change this out. So they look similar, right? I've got the hydrogen here, and I've got the CH3 here. Water is an essential liquid to support life. We all need water. Methanol is a poisonous liquid that will end up causing you to go blind. And this is different than drinking alcohol. Drinking alcohol is ethanol, where you have something that looks like this. So just adding that extra CH2 group, this is, and when I say non-toxic, this is relatively non-toxic. Ethanol is drinking alcohol. It is still toxic to the human body, but not in the levels that methanol is. So methanol, again, could cause blindness very readily, will cause you to get very sick. Ethanol certainly can cause you to get sick if you drink too much beer or too much wine or liquor, and it is poisonous. That's why you can get hangovers very readily when you get byproducts that this is, turning into. And we could talk about that more in an organic chemistry lecture when you get to that point. But the main point here is that changing these has a drastic effect on all of this, right? Here's water. You can drink as much of that as you want. No type of poisoning. Very important for life. Methanol, highly toxic to metabolic systems and can cause blindness. And then ethanol, a recreational drink that can cause altered states of mind. Certainly can be enjoyed, but you have to be careful because too much of it can be toxic. All three of these in different realms, just with the change of one small portionality there. All right. So let's take a look at another example. If I have O2, and again, this is not the proper structure of O2, but if I have two oxygens, right? What if I change let's just change an atom this time. What if I change one of those oxygens to a carbon? Well, now I have CO. This is carbon monoxide. Okay, so mono, where this is coming from, monoxide, meaning one oxygen. Carbon monoxide, well, we test for that all the time in our houses, in businesses. You have to be very careful of carbon monoxide because it's toxic. Oxygen, O2, is not toxic. In fact, we have to have it in order to continue living, right? We need to oxygenate our blood. We have the hemoglobin in the blood that'll help to bind to that oxygen, but oxygen is absolutely essential for the human experience in terms of living. Carbon monoxide is so problematic because it's so similar to O2. However, it does not provide the same oxygenation process to the body. It will competitively bind quite effectively to the red blood cells that are coming by to pick up oxygen. So you start breathing carbon monoxide in, this is going to compete with the binding spots for O2 and kick O2 sort of out as carbon monoxide comes in. And that can become problematic because you can slowly suffocate to death when you're not getting enough O2, but you don't realize it. It's not like somebody's strangling you and you're suddenly aware that you're not getting any oxygen whatsoever. So carbon monoxide can be a very dangerous poison that's sort of slow acting, competing with oxygen. Again, just a change in one atom, carbon versus oxygen. So maybe that can give you a bit of an appreciation for how delicate compounds are. If I change one atom out for another, I can have drastic effects. Now, this isn't always the case. Sometimes you can change an atom and absolutely no major effect is going to happen. That's certainly possible. But it's also possible that you change one or two atoms or a chunk or a portion of a molecule, and suddenly you have a completely different reactivity, biological functionality, all of that kind of stuff. Okay, so very important to understand. So the last thing I want to talk about here, and then we're going to sort of wrap up the first lecture. Let me come back here. Okay, is the states of matter. And there are, when I talk about this, we're talking about, again, from a chemistry standpoint. You can argue about plasma and all that kind of stuff, but there's three major states of matter that we're concerned with: solids, liquids, and gases. Those are the three. So what is the difference between these three? You probably have a sense. If I told you, bring me a solid, bring me a liquid, and bring me a gas, you would have a general idea or sense of what I'm talking about. But we want to classify this on a matter and an atom level because that's what we've been talking about in this lecture. So how do we sort of do a primer for those three? Well, here's what we're going to look at. A solid, all right, let me clear the whiteboard here. When we deal with a solid, solids are going to have atoms very close together. Very, very close together. So the atoms are close when we're dealing with solids. So again, if I pick something up that's solid, the atoms that make up whatever solid material I'm holding are very, very closely packed together, right? So if you were to draw these atoms, they barely have any room in between one another, right? And so one of the things that we talk about when we talk about solids is that they have a rigid form or a definite form. So what do I mean by that? Well, think about liquids versus solids. If I take this solid piece of material, right, and I place it into a container, it's going to maintain its regular shape and form. There's not going to be any sort of change there. However, if I took a liquid and I put it into a container, it is going to occupy the shape of the container. So liquids are fluid, they can morph, and we're going to get to them in a second. But when we deal with solids, they have rigid forms, right? They have basically, I don't want to say immalleable, because you can sort of break or shatter certain solids and break off chunks or pieces of them. But in general, if I set them down and I don't touch them, they're going to stay in that rigid format. They're not going to spread out or to change in any major way. So the atoms are tightly packed together. We have rigid form. And what the atoms are able to do at this state is that they can really just vibrate. So you can have motion in a solid, certainly not a liquid or a fluid motion. But these atoms that are close together, if you think of these both as atoms, right? If I come through and I strike something, if I hit my desk, or if I hit something else, those atoms can vibrate very quickly back and forth. And that is considered to be, on some level, movement between the atoms, right? And energy that's being transferred between the atoms. And you can get further and further into that discussion when you talk about physics and physical chemistry. All right, so liquids. All right. Now this is where a lot of students sometimes get confused. They think that the atoms in liquids are very far apart. Well, compared to solids, relatively speaking, they're actually still pretty close together. So the atoms are close. They are further apart than in the solids. So we will kind of add that. They are further apart, okay, than in the solids. So maybe I'm dealing with something like this, but they're still pretty close together. So we were just talking about how when we deal with liquids, they can occupy the shape of the container that they're put in. Okay, so that's important. But what's also important here is that when we deal with liquids, and we could also say this about solids, solids have a set volume, and so do liquids, right? So it's kind of weird thinking about volume when we talk about solids, but you can have volume for a solid. You usually deal with it in cubic centimeters. You don't deal with it in milliliters, whereas when you're dealing with liquids, you can start talking about dealing in milliliters or things like that. However, when we're talking about liquids and solids, if I have 5 milliliters of liquid, I could put it into a swimming pool or I could put it into a tiny little cup. I still have 5 milliliters of liquid, right? It hasn't changed the amount of volume. It simply changed the space that it's trying to occupy, right? So it can spread out a little bit more at the bottom of the container, but at the end of the day, I still have 5 milliliters, okay? So when we have volume here, right, set volume or constant volume when we're dealing with liquids. Now, gas. When we get to gas, okay, gases are going to have a volume that will occupy or spread, let's put spread to occupy, entire container. So what's the difference between this and a liquid? Well, let's talk about it. If I have a sealed box, right, and there's a lid to that box that I can open, if I put 5 milliliters or 25 milliliters of a liquid into that box and I seal it, I still have 25 milliliters of that liquid that's sitting at the bottom of that container. If I take gas and I open that container and I put a specific volume or set amount of gas into there and I seal it off, the gas spreads out. The molecules spread out to occupy the entire container. They'll try to, as evenly as possible, spread themselves out to occupy the volume of the container. And so that is different than a liquid. The liquid will morph to the shape of the container, all right? So maybe that's what we really want to point out here. It's the shape of the container that the liquid can morph to. It's the volume of the container that the gas can basically spread or occupy, okay? So gases can change their volume depending on the container that they're in. And so that's why you have compressed gas cylinders where we put them in a small amount. But if I open that gas cylinder and I let it completely bleed out into a locked room, then that room now contains gas all over the place, right? The gas has spread from that container to occupy the whole room. If I take a bottle of water and I dump it on the floor of the room, okay, negating evaporation or anything like that, I have a puddle at the bottom of the room. Right? The water molecules didn't spread out and go throughout the entire room when I did that. So, all right, we've got gas. It's a volume that's going to occupy, spread the entire container. And then we also want to mention that the atoms here are going to be very far apart. Right? So we've got atoms all over the place. And these atoms, they're going to move fast in comparison to liquids, where the atoms aren't moving super fast, but the atoms are fluid. So in a solid, they can only vibrate back and forth next to each other. In a liquid, they can kind of move over top of one another, right? So they're fluid, but they aren't able to break out and occupy the entire space of the room. Whereas a gas, you've got atoms that are moving very fast, bouncing off the walls of the container, going back and forth. And we will have an entire unit on gases where we focus on the pressure of gases, the volume of gases, all that kind of stuff. So that, I'm definitely going to cut it off here because we're running about 24 minutes in. That is a quick primer or beginner's course to general chemistry. All right. So in the next lesson, we will talk about chemical and physical changes. We're also going to talk about mixtures, homogeneous and heterogeneous mixtures, because you want to be able to tell the difference between those. So I hope you guys found this useful and helpful. I will probably post up some sort of a question review session so that you can practice what we learned here. But this is the first lecture in the general chemistry course, and I will see you guys for the next lecture. So thanks a lot and take care.